So for the third and final part here of homework 7-2, okay, so we'll see questions 11 and 12 in this one. Okay. These are two of kind of the more challenging torque problems probably as we look through this section, but if you can get pretty comfortable with these two questions, you really have a pretty good understanding of what's going on with torque. Okay, so a uniform beam of 1200 newtons, it's a piece of medical apparatus. Okay, it's just this device, they just give it that special name. 3.5 meters long, is suspended horizontally by two vertical wires at its end. A small but dense 550 newton weight is placed on the apparatus 2 meters from one end as shown in the picture. What are the tensions A and B in the two wires? So we're looking for what's the tension of A, right? We know that tension is a force, so we're looking for that force. And then what's the tension of B, so we're looking for that force. Okay. So we're looking up for those two forces. Obviously, one of the biggest pieces of information is that very first part right there. When it tells us there's a uniform beam or a uniform device with a weight, when it's a uniform device, we know that that weight is going to be applied at the center of gravity, which if it's uniform will be the geometric center. Okay, so this beam, the 1200 newtons would be acting exactly from the center of that. Okay, so it'd be acting exactly halfway, 3.5 divided by 2. Okay, so 1.75 meters from either side, right, of this medical apparatus. Okay. We also have the small but dense block sitting on it, so we also have this force of 550 newtons sitting on it. Okay, so I've got those two forces there pushing down, and then I've got the two tensions pulling up. So if I stay true to just forces, if I look at the net force, now in this situation, if the medical device, if the apparatus isn't moving, I know the net force needs to be 0. And what that tells me is the tension of A plus the tension of B, right, need to equal the 550 newton force that we have pushing down plus the 1200 force we have pushing down, right? We know that if those two forces, the two tensions pull up and these two forces pull down, those two are going to have to ultimately balance out. Okay, so the problem is if I look at this equation, I've got two unknowns, right? I've got the tension of A and the tension of B. Okay? And anytime we have two unknowns with forces, right, if I can't set up a system of equations, my best bet is probably going to be to take advantage of torque. Okay? So the idea here is I can use torque then to eliminate one of these two tensions. And the way that we can do that, if you've looked through some of the other problems, obviously you've seen this before, but the way that we can do that is if I put the axis of rotation at either point A or point B down here. So if I put the axis of rotation at either of those locations, I negate one of these two forces from the context of torque. Okay, so I'm actually going to go ahead and work with the axis of rotation over here with tension B. Only reason I'm going to do that is because they gave me the distances with respect to point B, so it's going to make my finding of the torque a little bit easier. Okay, so I'm going to choose that as my axis of rotation, which again means that for the purposes of torque, the second tension there, tension B, is not actually going to produce any torque since it's not at a radius, right? It's passing through the center of the rotation, so it's not going to produce any rotational torque. Okay, so now I only have three forces that are contributing to torque. I have tension over here A, and then I have these two forces of gravity which pull down. With respect to this axis, the 1200 newton force would cause it to want to rotate counterclockwise. The 550 newton would also cause it to want to rotate counterclockwise, which means because the beam is not rotating, the tension needs to be pulling up and it thus needs to be providing a torque that's rotating clockwise and balances these two out, right? So the big relationship here is if I know that it's not rotating, I know that my net torque needs to be 0, which furthermore tells me that the torque caused by tension A needs to equal the torque caused by, again, the block itself, so the block on there, and then the medical apparatus, which I'll go ahead and just call the beam, right? The metal beam that we have there. Okay, so the torques have to be balanced out. So then it's just a matter of how do we calculate torque. Okay? So my force, my tension in this case, times the distance, right? Times the distance to that point. The force of gravity of the block times the distance of the block, and then plus the force of gravity of the beam times the distance of the beam. Okay, so at this point, the good news is if we look at this, once again, we only have one variable. The first tension over here is the only thing we don't know. The rest of these are measurements that we do have. Okay, so TA times the full 3.5 meters, because that's how far it is from the axis of rotation. It's the full 3.5 meters away. Okay, so I'm going to use that entire distance. And then the force of gravity of the block is acting 2 meters away. Okay, so my 550 Newton block is acting from 2 meters away, plus the 1200 Newton beam. And again, the most important part, maybe the easiest part to overlook, is the radius of the beam. Since the beam is acting, the weight of the beam acts from the center of the beam. Since it's a uniform object, that's just 1.75 meters then from my radius, from my axis of rotation. Okay, so then solving for tension A in that scenario, again, all I'm doing is just calculating the numbers, so I'm just calculating this and solving, and I should get somewhere in the ballpark of about 914. Okay, so when I calculate this, I believe I get about 914 newtons. Okay, so that solves for my first tension. Now, finding the second tension, you could do another torque scenario. You could say, well, now let me reset and let me say that my axis of rotation is over here at A, and then do pretty much the exact same thing we did. But again, we don't have to make it that complicated. Okay, so if you've seen some of the other ones, seen some of the other examples here, you know that I don't have to make it that hard. Instead, if I just look at the forces, right, and I've actually already got that force relationship set up, I already know that tension A plus tension B needs to equal the total of those two weights pulling down. Okay, so for finding my second tension, if I just take advantage of this relationship, all I really have to do is plug in my first tension and solve for the tension of cable B. Okay, so if I do that, I just plug in 914 and then solve for the tension of cable B. I should get somewhere in the ballpark of 836. Okay, so about 836 newtons. So again, could you have done torque? Absolutely. You could have chosen this as the axis of rotation, gone from there, but I absolutely did not need to. I can just take a step back and do forces. Okay, so like I said, this may be one of the more complicated. As long as you know where to place the axis of rotation, though, you can eliminate one of your torques, one of your tensions, which makes it a little bit easier to work with. So then that brings us to our final question, question 12. So a meter stick balances at the 50 centimeter mark. If a mass of 50 grams is placed at the 90 centimeter mark, the stick now balances at 61.3 centimeters. What is the mass of the meter stick? It looks like a relatively simple problem, but there's definitely some big concepts we need to be comfortable with here. And the first of which is really just that first sentence. Okay, so they kind of give us two situations. That first sentence is saying if there's nothing else acting on the meter stick. Okay, so if I just have the meter stick, if it's hanging, I know that the meter stick obviously is 1 meter long, which would be 100 centimeters, right? And they tell me that the meter stick in and of itself balances at the 50 centimeter mark. So it balances over here at 50 centimeters. Okay. Might seem like a trivial point, but it's actually a very important one, because what that tells me is this is a uniform meter stick. If this meter stick is balancing at the 50 centimeter mark, then that tells me that the force of gravity, which is the only force acting on this, has to be pulling straight down at 50 centimeters. The reason I know that is if I put the pivot at 50 centimeters and there's no net torque, the only force has to be going through the axis of rotation. Okay, so the fact that there's no net torque tells me that when this pivot over here is at the 50 centimeter mark, that's where my force of gravity has to be applied. Now the reason that's important is, again, no matter what the context for the meter stick, so they tell us we put the pivot over here somewhere at 61 centimeters, but even if I put it at 20 centimeters, if I put it at 70 centimeters, 80 centimeters, wherever, no matter where I move the pivot, the force of gravity of the meter stick itself always needs to act from the 50 centimeter mark. Okay, so that's very, very important for our second part of this problem. Okay, so once we recognize that, this becomes a lot like the teeter-totter problems that we're used to. Okay, so we know that the force of gravity acts from the 50 centimeter mark. Okay, so my force due to gravity, regardless of the pivot point, is acting from here. They tell me that I put the pivot point now at 61.3 centimeters. Okay, so here's my pivot at 61.3. And then in order to make this balance, because right now if this was the situation, right, if my pivot was over here but the force of gravity was over here, we'd have a torque that causes the meter stick to rotate. It doesn't, because we've placed an extra mass, we've placed an additional mass over here at the 90 centimeter mark. Okay, so that 90 centimeter mark, that mass also pulls down, right? And the important concept here is that mass produces a torque that counteracts the torque of the force of gravity itself. Okay, so the reason it's so important is we need to recognize where the force of gravity is, we need to recognize where the mass is, because those are the only two forces acting, and they're the only two that generate then a torque. Right, they're the only two forces acting downward, I should say. The pivot would also be pushing up, but for the sake of torque, those are the only two about the axis of rotation. Okay, so Now if I just jump in with torque, I know that the torque caused by the force of gravity of the meter stick needs to be equal to the torque caused from that other mass. Okay, so the question asked me, what's the mass of the meter stick? Well, I need to find the force of gravity of the meter stick times the radius equal to the force of gravity of the extra mass that they've added times the radius to that mass. Okay. Biggest thing to watch out for here is, again, the radius, right? The radius does not just mean the 50 centimeters, the 90 centimeters, 61.3. It's the distance from the pivot point. Okay, so the center of mass acts 11.3 centimeters. 11.3 centimeters is how far it is from 50 to 61.3, right? So this acts 11.3 centimeters away from the center of rotation, whereas the 90 centimeter mark would be, what is that, 28.7, right, centimeters away from the axis of rotation. Okay. Here's the good news. Because both sides are in centimeters, you actually don't have to convert it to meters. If you would like to, there's obviously no problem with that. Okay, so if you want to put this in 0.113 meters and this in 0.287 meters, you absolutely can. I actually don't need to, since both sides have that same conversion. Okay, so breaking this up, this would be the mass of the meter stick times gravity times, again, the 11, I'll go ahead and use in centimeters just to show us. So the 11.3 equals the mass of the object, which we probably do want to go ahead and convert that to kilograms, although you don't necessarily need to. That would just give you the answer in terms of grams. But since our standard unit for that is kilograms, I'm going to go ahead and convert that. Okay, so it would be my mass of the object, which is 0.05 kilograms, times, again, the acceleration due to gravity, 9.8, and then times the distance away, which in this case would be 28.7, since I'm working with centimeters. Well, gravity cancels out on either side, and obviously looking through even without that, we see that we only have one unknown. Okay, so the mass of the meter stick is easy enough to solve for. Solving for the mass of the meter stick, just calculating this, I should get it that it's about 0.127 kilograms. Okay, so another example of obviously using torque. The reason this one's a little bit tougher, right? It's a relatively simple looking problem. It's just got a couple pieces of information, but it's that key part right there, right? By telling me that it balances at the 50 centimeter mark. If instead of that first sentence, if I had told you that a meter stick were to balance for some reason at maybe the 60 centimeter mark, then it would just tell me that the meter stick wasn't uniform. It would tell me that the center of mass for that meter stick had been over here at 60 centimeters instead of 50. Okay, so we still would have been able to work this problem, just would have had to keep that in mind as we go through. But anyway, hope this helps. Again, this is the completion of the second homework assignment. Okay, so if you do have any questions, obviously beyond this, feel free to let me know, but hopefully this helps you if you got stuck on a problem or two.